So hello everyone. Today we'll be solving some practice questions on the GATE DA paper, the GATE Data Science and Artificial Intelligence paper, especially question number 53. In this video, we will look at the different concepts that we can learn from this set of lectures and from this lecture. So my goal is not just to solve the question, but also to help you to understand the underlying concepts behind those lecture, behind the question. So I hope this is helpful. My name is Aditya Agrawal and I'm a recent graduate from the Indian Institute of Technology, Madras. So the question says that let S square be the variance of a random sample of size n greater than 1 from a normal population with an unknown mean mu and an unknown finite variance sigma squared. Consider the following statements. Number one, S square is an unbiased estimator of sigma squared and S is an unbiased estimator of sigma. N minus 1 by n s square is the maximum likelihood estimator of sigma squared, and root over n minus 1 by n s is the maximum likelihood estimator of sigma. Which of the above statements do you think is true? Is 1 only true, B 2 only, C is both 1 and 2, and D is neither 1 nor 2? So let's start with the very small, very basics, right? First, let us understand what is an estimator. Then let us understand what is an unbiased estimator, right? And then we will look at what is a maximum likelihood estimator, and we'll derive these different derivations so that you are better understand these things. Okay. So what is meant by things here is you have your population, which consists of all the objects in the universe. So this is the population. It consists of objects capital X1, capital X2, so on till capital Xn. And all in all, population parameters cannot be observed. You cannot measure the population mean. You cannot take all the, let's say this xi denotes the individual weight of a person. Then you wouldn't actually go ahead and measure the weight of every person in this universe and tell that the average weight on earth is X, right? So what you do is you do something called sampling, where you take a representative subset, let's call it Si, from the population P, and that is called as a sample. And the sample contains of some set of little n points from x1 till xn. Okay, fine. So your population you cannot be observed, but your sample characteristics can be observed. Okay, so what do I mean by this is, for example, if you have your sample, you can calculate something called the sample mean, denoted by x bar, which is nothing but 1 by n summation I equal to 1 to little n xi, right? This you can estimate using the sample you see. So this, by using this measurement, you can estimate what will be the mean of the population, which means this is called an estimator. Okay, and an unbiased estimator would mean that the expectation of any estimator should be equal to the population parameter, which also means, let's take the sample mean in this scenario. So the expectation from the sample mean is nothing but the population parameter mu. What do I mean by this is, it means if I, let's say, sample some set of n different, if I take n different samples, so this is S1, this is S2, this is S3, and if I take the expectation across each, the mean of across each sample, then what I should expect is it should be equal to the population parameter mu. Okay, and if it is equal to the population parameter mu, then I say that it's an unbiased estimator. And this is what we want also, right? We were not able to estimate the population parameter mu, but instead we took a sample, and what we expect is the expectation of that sample mean should be equal to the population parameter. Similarly, the variance of the sample should be equal to the sigma squared. Okay, and also expectation of each xi, or the average across each data points xi, should be equal to mu as well. So now first what we will do is we'll try to see that the expectation of x bar equal to mu is a unbiased estimator. So let us prove this thing. Okay. So expectation of x bar, I can write this as expectation of 1 by n summation of I xi. So I just use the formula of mean that I wrote above, sample mean x bar above. I can bring the 1 by n out because it is a constant. 1 by n um, summation of expectation of xi, right? And now the expectation of xi is actually mu, right? So what I can write is 1 by n summation of I n, mu, and summation of I across mu is n mu. So n mu by n, which is nothing but mu. So I can say that my expectation of x bar is nothing but mu. Okay. Now you might be saying that, okay, this is okay, but can you give an example of a biased estimator, right? So let me take a small example of a biased estimator. So everyone knows that the sample variance is, the formula is 1 by n summation of I xi minus x bar squared, correct? Right? So if you are paying attention, then you see that this formula is incorrect because the sample variance is not 1 by n, it is rather 1 by n minus 1, right? But let us deliberately make the mistake and say that it is 1 by n. Now, the variance of s square, oh, sorry. So if it is an unbiased estimator, then the expectation of s square should be equal to the population variance sigma squared, correct? So let's see if we get this or not. So expectation of x square, I can write this as 1 by n, right? And then expectation of sum equal to I equal to 1 to n xi minus x bar whole squared. So I just substituted the formula for s square and brought out the 1 by n outside because it's a constant, which is equal to 1 by n, okay? Expectation of summation of I equal to 1 to n. Now I can expand this square out, so xi squared minus 2xi x bar plus x bar squared, right? Which I can write this as 1 by n expectation of. So, okay. So over here, what I can do is I can take the expectation term inside and write this as expectation of I e of xi squared minus 2. And now what I will do for the middle term is I will multiply it by n and divide by n. Okay. I will explain why I'm doing. Just hold on for some time. Okay. Okay. Maybe I'm jumping some steps. Maybe I'll do it from the start. If you don't. So 1 by n expectation of I equal to 1 to n, right? And then what I will do is xi squared right, minus 2n x bar. So what I'm doing for the middle term is I'm multiplying by n and I'm dividing by n. So this is summation of xi by n, right? Okay, maybe I'm okay. Let me create some space, right? So, right. So what I'm doing is plus summation of I x bar squared. Okay, so I just in put the summation inside. Now what is xi by n? So xi by n, summation of all data points xi by n is your sample mean, right? So I can write this as 1 by n expectation of summation I. So I'm just writing I equal to 1 to n in short as summation of I minus 2n x bar squared plus I can move the x bar squared out from the third term because it is not dependent on I, and summation of I from 1 to n is just n itself. So minus 2n x bar squared plus n x bar squared is minus n x bar squared. So and also I can move the expectation term inside now. Okay, okay, right. So now my job is to only estimate the value of expectation of xi squared and expectation of x bar squared. So to estimate the value, I'll just do some small recapitulation of uh, probability. So let me use a different color for that. So the variance of xi, right? What is the formula for the variance of xi? Expectation of xi squared minus expectation of xi whole squared. Correct? So variance of xi is nothing but sigma squared from the previous equation. Expectation of xi squared minus expectation of xi is mu. So this becomes mu squared. So expectation of xi squared is sigma squared plus mu squared, right? And what will be the variance of x bar? Variance of x bar is, again, you will just replace the xi with x bar. So expectation of x bar square minus expectation of x bar the whole square. Okay. And this is nothing but, so this is sigma squared by n. Okay. Why is it sigma squared by n? Let me do that quickly, the derivation. So the variance of x bar, okay, you can also write this as the variance of x1 plus x2 plus dot 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 xn divided by n, right? And when you move the 1 by n outside, it becomes a squared because of the variance term. So this is 1 by n square, the variance of x1 plus x2 plus dot 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 xn. Now you can move the variance term inside and say this is nothing but the variance of x1 plus the variance of x2 plus dot 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 the variance of xn. Now each of these individual variances is nothing but sigma squared. So if you sum over all n sigma squared, then you get n in n times sigma squared. So this is nothing but 1 by n square times n times sigma squared, n cancel, and you get sigma squared by n. Okay. So sigma squared by n is equal to, what is the expectation of x bar square minus the expectation of x bar is mu square. Why is expectation of x bar mu? That is the unbiased estimator formula we proved, right? Okay. And now what will be the expectation of x bar square is nothing but sigma squared by n plus, sorry, mu squared. Expectation of x bar is mu, so square will be mu square. Now what I will do is I'll just plug in the values of expectation of xi square and x bar square in this equation, and what I get is 1 by n summation of I. Expectation of xi squared is sigma squared plus mu squared, right, minus 2n times expectation of x bar squared is sigma squared by n plus mu squared, right. Finally, what I will do is I will write this as 1 by n summation of I sigma squared plus mu squared. They are not dependent on xi, so I can write this as n of sigma squared plus n of mu squared minus 2 of sigma squared minus, okay, I might maybe I'm missing some step here. Okay, let's see, minus 2n of mu squared, right. I think I'm missing a step. Wait a second, guys. Psi x bar, right. Okay. So what I did wrong was, so minus 2n x bar square plus x bar square is n into x bar squared, right? So that is a mistake I did. So this 2 won't come in, right? Okay, sorry about that. And so finally I can move these terms a bit on the side. Okay. Okay. So understood the mistake, right? Minus 2n x bar squared plus x bar squared n would be n of x bar squared n. So this is nothing but 1 by n and mu squared get cancelled, and you can write this as n of sigma squared minus sigma squared, which is equal to n minus 1 by n times sigma squared, which is the wrong, because my expectation of s square should have been sigma squared, right, for it to be an unbiased estimator, but we are trying to underestimate the population parameter sigma squared by n minus 1 by n, by the factor n minus 1 by n. And if you see carefully, if I would have, oh sorry, if I would have given the correct formula for the sample variance, which is n minus 1, then all of this would have been n minus 1, right? All of this would have been n minus 1, n minus 1, n minus 1. All of this would have been n minus 1, right? See, all of this would have been n minus 1, 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 and this would have been also n minus 1, and n minus 1 by n minus 1 you can just make it as 1, and then you get sigma squared, correct? But since your formula you considered 1 by n rather than not 1 by n minus 1, your expectation of the sample variance s square was not equal to the population parameter sigma squared. So let's come back to the question. So we can claim that the s square is an unbiased estimator of sigma squared, and you can take the square root and you will get s as an unbiased estimator of sigma. So one is definitely the true, right? One is true. Now how about the second part of the question, right? The second part talks about something called MLE, which is a maximum likelihood estimator. So and it's given that it is a normal distribution. So from a normal population with an unknown mean mu and an unknown finite variance sigma squared. So the expectation of an individual data point xi is nothing but mu, and expected variance of individual data point xi is nothing but sigma squared. That is also one of the reasons behind it. Now, when I talk about maximum likelihood estimator, right, what we do is we try to find out, given a data point x, what is the likelihood of the parameters mu and sigma, which means This is nothing but 1 over root over 2 pi sigma squared e to the power minus 1 by 2 x minus mu over sigma the whole square, right? So what it means is we try to find out that given a data set, data point x, what is the most likely value of mu and sigma, correct? So what do I mean by this is, so let's say if I have a data point something like 100 here, right? Just say I have only one data point here, then my best case of normal distribution I can estimate is this, with my mu as 100 and some sigma as some maybe, I don't know, some 10 or something, right? Or something like that, okay? But that is what I'm trying to do here. Given the set of data points, what is the most likelihood parameters of the distribution mu and sigma? Now my x is just a single data point, but typically you have a set of n data points. So x1 till xn, okay? And then what you do is, what the maximum likelihood estimator here allows you to do is, since each data point you claim is drawn IID from the population distribution, IID means independently and identically distributed. If each data points are independent, then the likelihood for each data point is a product. Likelihood for the entire set of data points from x1 to xn is nothing but the likelihood across each product of the likelihood across each data point. Okay, let me repeat. You had your dataset X, which consists of n samples from x1 to xn. You want to estimate the most likelihood parameters of mu and sigma given this set of data points. What the maximum likelihood estimator tells you is, since you have drawn this samples IID, right? You have drawn the samples X IID from the population distribution P, then they are independently distributed. So the likelihood across all data points is nothing but the product of likelihood across each data point, xi. Okay, so this is the product sign pi I equal to 1 to n L of mu comma sigma I. And what I can do is I can substitute the value of L, right? And say this is nothing but 1 by root over 2 pi sigma squared times e to the power minus 1 by 2 x minus mu by sigma the whole square. Now there is typically one thing that you can do here, which is the both the functions, the product, this function L as well as the log, they all maximize at the same point. So I can take the log likelihood of this function L, and this product now converts it into a summation. Okay, why does it do that? Again, if you had if you had okay if you had a times b times c, okay, then if I take the log now, it will become log a plus log b plus log c, right? So this is the same concept. So the products became summation. So the summation of log of, again I'm taking the log base e. Why I'm doing it, I will explain. 1 by root over 2 pi sigma squared multiplied by e to the power minus 1 by 2 xi, so this should be xi minus mu by sigma the whole square. Okay, okay, fine. So what I can do now is, since there is a multiplication term here, right, I can again use the property log a times b and split this into 2 as log a into log b. So this is nothing but summation I equal to 1 to n log base e. Okay, let me write this in bracket, right? So log base e, again 1 by x, I can write this as x to the power minus 1. So I can write this term as 2 pi sigma squared to the power minus 1 by 2 plus log base e to the power minus 1 by 2 xi minus mu by sigma the whole squared. Now log base e of e to the power x is nothing but x itself, right? So what I can do is the next step will be I equal to 1 to n, and also the log of a to the power b is b log a, so that I can bring the power down, so minus 1 by 2 log base e 2 pi times sigma squared plus, I can say, okay, so this is plus, and if you write log base e to the power x, so this whole term here, which is um, this term here, right, will just come down, and there is a minus sign leading this term, so that's why I can write this as a, that's why I can write this as it is, as minus 1 by 2 xi minus mu over sigma the whole square. Okay, so far so good. Now I can again use the log function to break this 2 pi into sigma squared. Okay, 1 by n minus 1 by 2 log base e 2 pi, right, plus, so it will become minus because it's a minus term outside, so minus 1 by 2 times 2 log base e of sigma. So it's log of sigma squared. Again, you can use the power rule and bring the 2 out, and you can make this as log sigma minus 1 by 2 xi minus mu by sigma whole squared. Okay, so you can cancel out the 2's here, and you get I equal to 1 to n minus 1 by 2 log base e of 2 pi minus log base e of sigma minus 1 by 2 xi minus mu by sigma the whole square. Okay. Now, why was I doing all these things all this while? So what MLE says is, once you have found the likelihood function, let's say this is my likelihood function, right? This part. So this is my likelihood function, right? Now it consists of two parameters, and what I do is I take the partial derivative across each parameter, equate it to 0. So dl by d mu, I equate it to 0 and find the value for mu for which this function is the maximum. How can I say it's a maximum? If you take the second derivative with respect to mu, then it should be less than 0, right? And dl by d sigma, okay, dl by d sigma, you will equate this to 0 to calculate the value for sigma for which the function is maximum. And to find whether it's maximum, you can do dl by d sigma squared less than 0, right? Now all these derivatives will be much difficult to compute if we had this function, that is the function that is shaded here. So that's why we try to simplify it, and this is the simplified version of the function. Now with this we had here, what we can do now is we can equate this, we can take the partial derivative of dl with mu, right, and we get this as, so in when we are doing the partial derivatives, when I'm differentiating with respect to one parameter mu, the other parameter is constant. So the first term is anyway a constant, so it is 0. Second term is also a constant because sigma is a constant here. The third term will be expanded, which is you can apply the chain rule, minus 1 by 2 xi minus mu by sigma right? Xi minus mu by sigma times 2 times minus 1. So you consider, so how do you take the chain rule if you have forgotten? Then you consider this term as a single unit, let's say y, so or mu, and what will be the differentiation of this with respect to mu? Mu squared, it will be 2 mu. So 2 times xi minus mu by sigma, and then inside you will see you will have to take a differentiate this term because 1 by sigma is anyway a constant. So xi minus mu is minus 1, right, with respect to mu. This is nothing but equal to 0. Okay. Okay. This is nothing but equal to 0. So if I clean this up a little bit, I get summation of I. Okay. Minus minus becomes plus. 2 can cancel. So this is nothing but xi minus mu by sigma is equal to 0, right? And if I'll just write it here, so I can write this as summation of I xi by sigma, right, minus summation of I mu by sigma is equal to 0. Then I can take the term mu by sigma that side, and summation of I mu by sigma is n mu by sigma. So this is nothing but 1 by sigma summation of I xi is equal to 1 by sigma times n. Sigma and sigma can cancel, right, times mu, right? So my mu is nothing but 1 by n summation of I xi. And what is mu here? What is 1 by n summation of I xi? It is nothing but the sample mean, right? So I can say that the maximum likelihood estimator for the population parameter mu, or let's say mu bar, is nothing but the sample mean x bar in this case, right? Okay. Sorry, you might have heard some background noise. Just ignore that. Okay. So dl, and now what we do is we take the partial derivative with respect to sigma. Okay. Good timing though. Okay. So if I do that, then my mu is a constant. So summation of I, first part is a constant. Second part is 1 by sigma because log base e of x differentiate with respect to x is 1 by x, right? And the third part is very simple, minus 1 by 2. Xi minus mu comes out because it's a constant. I can write this as sigma power minus 2, right? Sigma squared. If I bring it up, so I can write this as minus 2 times sigma power minus 3, right? Now this I can again equate to 0 and I get summation of I minus 1 by sigma. This will become plus 2 can cancel. Xi minus mu by sigma cube and xi minus mu whole squared is equal to 0. I can say that this is nothing but minus n by sigma because summation of I, and I can take this term that side. So this becomes, okay, sorry, 1 by sigma cube summation of I xi minus mu whole squared is equal to n by sigma. Sigma and this sigma can become 2 now, and this is nothing but sigma squared is nothing but 1 by n summation of I xi minus mu the whole square. And what is the mu that I found from the previous derivation? It's nothing but x bar. So I can write this as sigma squared is nothing but 1 by n summation of I xi minus x bar squared. Now if I ask you, is this a unbiased estimator? It's actually a biased estimator. Why? We just looked at it in the previous few minutes back. But so if I multiply this equation on the top and bottom by n minus 1, so this is 1 by n minus 1 of I xi minus x bar the whole square. And this term here is what? Anyone? If you know by now, very good. This term is my sample variance, right? This term here is my sample variance sigma s squared. So this is nothing but n minus 1 by n times s squared. So what is the maximum likelihood estimator of sigma squared? N minus 1 by n times s square. So the second option says n minus 1 by n s square is a maximum likelihood estimator for sigma squared. And if you take the square root, then it will be root over n minus 1 by n s is a maximum likelihood estimator of the standard deviation sigma. So 2 is also correct, which means your correct option is option C. Okay, so I hope you understood the concepts in this question. I tried to derive each and everything as much as possible. And if you want me to do any more videos, any particular problem, if you want me to solve, please feel free to comment down below. Please like and share and subscribe to this channel for more videos in the future, and also that helps to motivate me to create such more videos. I will try to create more videos for explaining these concepts in depth, and that will help you to be set for the exam as well. And this question was not very easy, to be honest. The derivation, I will suggest you to do it once again, right? To start from the top and then go to the bottom, and then that will help you to perform better in the exam. And with this, if you guys have any questions, feel free to like and comment down below any feedback you want to give me for my teaching, for my anything, and how can I improve, or anything that is missing. Feel free to comment down below, and I will make sure that is addressed in the next video that comes up in the near future as well. So with this, I thank you all for listening to me for this set of some few minutes, 30, I guess 30 minutes or so. And I hope this makes your concepts much clear. Thank you for watching.